Today we're going to have a little discussion about linear approximations and differentials. They're not difficult, it's just another way that we can estimate some values without having to derive at a location that it cannot be derived at. Before we dive right in, let me talk in general about a linear approximation. A linear approximation is when you use the tangent line at a point to estimate a value. So, for instance, we know the value at A. I think that says A right here. We know the value at A is this value. But if we wanted to estimate the value right here, and we couldn't plug it in, we could use the tangent line because the tangent line and the curve are very close to each other. So it would be easy to use the tangent line, and we would get a value that is relatively close to the actual value because those x values are close together. So, formula for a linear approximation is L of x equals f of a plus f prime of a times x minus a. Now, why is that? Well, it's because if we're at the point A, we know its y value is f of a. We know that the slope is going to be f prime of a. And if we use point slope form and plug these things in, we get y minus f of a equals f prime of a times x minus a, and we end up with y equaling f of a plus f prime of a times x minus a when we move our f of a across the equal sign. So that's why it works. But what a linear approximation really is just the tangent line to the curve at a point. So let's try one. Find the linearization of f at a. So first thing we need to find is f of 1. Because our a value is 1, we need to get our point. We know our point is going to be 1 something. Let's figure out what that something is. So, radical 1 plus 3, which is radical 4, which is 2. So our point is 1, 2. Now to get the slope, we first need f prime of x, which is going to be 1/2 times x plus 3 to the negative 1/2. When we plug in our 1, so we can find the slope at this particular point, we get 1 over 2 times radical 4, or 1/2. Remember, you can pause and write these down at any point. So, we have our point, 1, 2, our slope, sorry, not 1/2, 2 times radical 4 would be 4, 1/4, x minus 1. And we end up with, when we simplify, 1/4 x plus 7/4. And we could use that line to estimate the value of some functions at other places. So like if we were trying to find 1.1, it would be hard when we plug 1.1 in for x to take the square root of 4.1. But we could probably more easily plug 1.1 into this line, and would it be exactly the right value? No, but it would be close. So it would be a pretty accurate approximation. Differentials are a little bit different if, and this is a new idea, this dy dx isn't necessarily stuck together. It's actually represented by the change in y over the change in x, because it's slope. How do we find slope? Change in y over change in x. So it really is just slope, and it can be moved. You can multiply both sides by the dx. So let's try one. It says find dy if y equals sine of x, and x is pi over 6, and dx is negative 0.01. So, first thing we derive, dy dx is going to equal cosine of x. We're finding dy, so let's solve this for dy. We get cosine of x dx. So dy is going to be cosine of pi over 6 times negative 0.01. And we radical 3 over 2 times negative 0.01, or approximately negative 0.00866 as our value for dy. Here's a real life one. It says the radius of a sphere was measured and found to be 21 centimeters. With a possible error in measurement of at most 0.05, so r can change by 0.05. What's the maximum error in using the value of the radius to compute the volume of the sphere? Volume of a sphere, 4/3 pi r cubed. We need to derive. We're deriving v in terms of r to get 4 pi r squared, which means dv equals 4 pi r squared times dr. Plug in our 21, plug in our 0.05, and this works out to be 277.088. So our maximum error, if we are exactly 0.05 away, which is the farthest away we're allowed to be, our volume will be 277.088 centimeters different than if we were right on at exactly the 21 centimeters. Now, let's talk for a second. dx and change of x, like it says at the top of your notes, are equal. They're always the same because it's independent. We decide what that is most of the time. dy and y are a little bit different. dy is the estimated difference. Notice how when we move over to this next x value, dy is the difference between this y value and the y value on the tangent line. So it is the estimate. Change in y, on the other hand, is the actual change in y, because it is from the actual y value at x and how much it changes to get over to this next value where we moved over a change in x value. So know that change in x is exact and dy is estimated using the tangent line. So says compute change in x. Well, change in x is exact. So when x equals 1, y equals radical 1, which equals 1. Then they tell us we change x by 1. So our next situation, when x is 2, we change by positive 1, it goes up 1. If it were by negative 1, it'd go down 1. Then y equals radical 2, which means y changed from here to here. It changed our change in y to be exactly correct is radical 2 minus 1, or approximately 0.414. We're going to see in a second how close that is to the actual truth. Notice these are exact y values that we subtracted to find the change in y. Now, if y equals radical x, that means that dy dx equals 1/2 x to the negative 1/2, or 1/2 radical x, which means that dy, our estimation, using the tangent line, because we derive, we're using the tangent line at whatever value we plug in for 1, or for x, I'm sorry, which is going to be a 1, times our dx. So dy is 1/2 radical 1 times 1, or 1/2 is our value for dy. Now dy is an estimation. Is 1/2 close to 0.414? Yeah, pretty close. So it was a relatively good estimate. Now picture-wise, here's what this means. We've got this function, change in x, let's say this is 1, and then 2 would be over here, and our differential dealt with, that's not a good tangent line, let me try again, dealt with our tangent line. So this is our y value at 1, and if we go up to where the y value is here, this is our exact change. So it's going to be change in y. That's exactly how it changed. Now, using this tangent line, which is what you use when you use a differential or a linear approximation, that is our dy. So there's the difference there. Change in y is the actual change, while dy is the estimation at that point using a tangent line. Now, let's try an example. So, if we've got radical of 99.8, our equation is radical x. Now, I can't square root 99.8, you probably can't either, but there is a number close to 99.8 that we can square root, and that is 100. So we're going to use 100 to estimate. To get from 100 to 99.8, that means our change in x, or our dx, has to be negative 0.2. So, let's talk about this. We already derived this on the previous page to get 1 over 2 radical x. And that means dy is 1 over 2 radical x times dx. We figure out what this equals. We get 1 over 2 times radical 100 times negative 0.2. Or 1 over 2 times 10. And negative 2 tenths would be negative 1 over 5. And we get a value of negative 1 over 100 as our dy. So that's an estimation of how it changed. So we estimated that when x was 100, we did a change of x of negative 0.2 to get x to be 99.8. When x is 100, y is 10. We discovered that our dy is negative 1 over 100, which means our estimated y value when x is 99.8 would be 9 and 99 100ths. And this is our estimated value. Watch this again if you need to. If you have questions, bring them with you to class tomorrow.